record. So it's on the record. So we're going to study complex numbers. It's written as x plus iy. So how many of you have learned complex variables during your high school days? No? And freshman calculus? So it's totally new topic for you? You never heard about it? It's a disaster of education system. You're supposed to know at least what is complex numbers from high school days. So x and y belongs to set of real numbers. I is something that I square is minus 1. Okay, let me rephrase my question. So, how many of you know what is real numbers? So, what is real numbers?
Not measuring. Something that is measuring.
No. So, what is real number? Anybody knows the definition of real numbers? You didn't learn in high school again? Another disaster of education system. So real number is a rational number plus irrational number. Okay, so I'm going to ask again. So anybody knows what is the definition of rational number? Rational number in Korean is called yurisu. So anybody knows the definition of rational numbers? Okay. Okay, you're close. So what is the numbers you can put in the denominator and denominator? Integer. So apparently your math education is quite flawed. So maybe we have to start from the scratch. So say Q is a set of rational numbers. Then Q, which belongs to this set, is written as m over n. And m, n are integers. So do you know what is integer? So what is, anybody knows the definition of integer? So what is the definition of integer? 정수, 정의. Anybody can claim or say or clarify the definition for us? Okay, integers, and n is not 0. So we say n m belongs to new set called integer. Oh, it's a set of integers. Actually, you learned about integer when you are in maybe 3rd grade. 3학년 초등학교. Okay, let's say okay, so let's trace back to the most elementary set of numbers, natural numbers. So anybody knows about natural numbers? It's called 자연수. if you don't know the definition of natural numbers, then I think something is very wrong. Because you have been learning since your maybe kindergarten, because of the early education 조기교육. Just follow me. Natural number is 1, 2, 3, 4, 5, etc., etc., right? So natural numbers, we are going to define n as a set of natural numbers. So we are using natural numbers based on base 10. That is, we are counting natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you go to the next stage, 11, 12, 13, 14, right? And do you know why we have a base 10 number system? Yeah, we have 10 fingers. Of course, some of us have 6 fingers, but 11 fingers, but very rare. So most of us has 10 fingers total, right? So instead of me teaching this class, if somehow the event of evolution has been different from now, and if not quite a good picture, if so if the evolution process has been different, if the big comet hit Earth in 65 million years ago didn't happen, then instead of us, maybe some of the dinosaurs were evolved as intelligent beings, most likely Velociraptor. So he's teaching here math, and we have dinosaur students. And the number system will be based on 6, because dinosaur has only 3 fingers. So dinosaur might have 6 number systems. So reptiles may have number system based on 6. So natural numbers actually evolved with the history. It's very natural. And it appears about maybe 200,000 years ago. So we did natural numbers. Maybe dates back to 200,000 BC. When our ancestors, your fathers' lived in the cave, and maybe there was other group, and your ancestors lived in the seashores. So there was one group of ancient us. They catch rabbit, and there is another group of people living in the seashores. They catch fish. So mostly cave dwellers eat rabbit all the time, and the seashore dwellers eat fish all the time. So what happens if we eat fish every day? You want something else, right? So they decide to meet in the middle ground and decide to change rabbit and fish. So what would be the most fair way of trading fishes and rabbits? The simplest case is 1 fish for 1 rabbit, right? So if there are many fishes and many rabbits, so you have to count. What do you do? So 1 fish for 1 finger, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if there are more fishes, what do you do? If there are more than 10 fishes, what do you do? to bring your friends, right? And then use his fingers to continue to count. And your ancestors in the cave do the same thing. So they use our fingers to symbolize the rabbit or fish. They become natural numbers. So it always starts with the 1, right? Because 1 fish for 1 finger. So 1, 2, 3, 4, 5, 6. So natural numbers is a very interesting property. You can add to natural numbers. So 2 rabbits with the 3 rabbits become 5 rabbits, right? So we can add. 2 plus 3 is 5. Or we can even multiply. Okay, we have 2 fishes in 3 groups. What is the total? 2 times 3 is 6, right? 2 times 3 is 6. It belongs to natural numbers. Oh, but by the way, subtraction. Sometimes work, sometimes not. If you have 3 rabbits and I want to give 2 away, how many are left? 1, right? I have 3 rabbits, I want to give 4 away. What happens? No rabbit to give, right? So there is no natural numbers. So 2 minus 3 actually does not belong to natural numbers. So natural number is not closed on subtraction. So we say if you do some operation like addition or subtraction or multiplication or division, and if the result is belongs to the same number system, we say that that particular mathematical operation is closed for the number system. So it's closed to addition and multiplication, but not to subtraction and division. So for almost 200,000 years, our ancestors has been working with the natural number system, which is close to only for addition and multiplication, but not for subtraction. So first number system that is close to subtraction is called integer. There is, according to the legend, that the Indians discovered that about 2,000 years ago. So integers is natural numbers plus 0 plus negative of natural numbers. So integer consists of minus 100, minus 99, etc., minus 1, 0. You go further, 1, 2, etc., etc. So there are actually infinite number of integers. And this is a very important number system. And it's addition, multiplication, subtraction can be defined on this number system, but not division. So if we divide by 2, 3 is not integer, right? And this particular operation with division becomes important. Important after the first industrial revolution. Do you know what is called the first industrial revolution? You didn't even learn history either? 신석기 혁명. Because before that, our ancestors lived in caves or lived in tea shores. They were collectors, hunters, collectors. But after Neolithic revolution, it's called the Neolithic revolution called the 신석기 혁명. They discovered farming. So you can grow crops. So that happens around 10 BC, about 10,000 BC. And gradually, the tribes become some ancient kingdoms. And by the time the 10th century BC, the set of ancient kingdoms has been established, right? So if you haven't taken any history class in high school, but maybe it's a good time to go back to learn something. So around 10th century BC, the ancient kingdom appeared. So what is the major income of those kings at the time? Well, right, tax. The tax become very important. The tax from the harvest, right? But taxation, in order to tax has to be proportional to the area of the land, right? It's proportional to the area of land. And if you have some given amount of land, it's divided by many people, then you need to count exactly or accurately the area of the land, right? So in order to do that, you need to be able to divide. So division becomes very important. And so is the geometry. So it's no wonder by the time of about 10th century BC, both in China and in East and West, there are the mathematics about those rational number systems and geometry appeared. So in ancient, in Greek, they called Euclidean geometry, Euclid. On the West, and in the East, there appear several mathematics books called 주비상전, 주비산경, or 구장산술. It's about BC 10th century. So they both deals with geometry and rational number systems. Geometry as well as the rational number system. So this become Q. So rational number system is the first number system which is close to the four basic arithmetic operations: addition, subtraction, multiplication, and division. So they thought these are perfect numbers. So by the time 10th century BC, the rational number system was known. And it is obviously closed to 4 basic arithmetic operations: plus, minus, multiplication, and division. And why 4 basic arithmetic operation is so important? Because with that you can define functions. For example, let's consider the Taylor series. Sine x is x minus x cubed 3 factorial plus 5 cubed factorial x to the 5th, etc., etc. So you can see that this is a subtraction, right? This x to the cube is multiplication. X times x times x, right? This is multiplication. This is addition. This is what? Division, right? So in order to be able to define functions, we need to find the number system which is supposed to be close to the 4 basic arithmetic operations, which is addition, multiplication, subtraction, and division. And that's the reason why you have been learning so hard since your kindergarten to learn how to add two numbers, how to multiply two numbers, etc., thing. Because those 4 basic arithmetic operations is the essential part of the definition of functions. So by the time BC 10th century, that the people knew that we have perfect number systems. It's called rational numbers. And so they thought that rational number system is the basis of all our universe, even then. But someone actually asked the question, is that so? Is there any other system which is also close to the 4 basic arithmetic operations? And that particular person is BC 2 century, and you know his name. His name is Pythagoras. Pythagoras. Anybody knows about the Pythagoras? Raise your hand. Oh, in Korean it's called Pythagoras. You know? Anybody knows Pythagoras? Raise your hand. Okay. So its actual name is Pythagoras, but okay. So he asked the following question: is there any rational numbers such that q squared gives 2? Answer is no. There's no rational number system that gives that, right? So we now know that it's q. So no q. No rational number systems So he invented a new number system called irrational numbers. So he said square root of 2 is the answer. And so Pythagoras actually thought about new numbers. X is a plus b square root of 2. A, b belongs to the rational number systems. So we call this is real numbers. So Pythagoras called x as real numbers. And this is set R. And many Greeks didn't like Pythagoras. So there is a rumor that Pythagoras was assassinated. Assassination means 암살, by the phonetic mathematicians who believed that the rational number system is the basis of the universe, and Pythagoras was like creating some chaos in the perfect system. So the rumor says he was assassinated because of the invention of the irrational number. How sad. So we can check whether this system is, we can define, is close to the four basic arithmetic operation. So let's say x1 is a1 plus b1 square root of 2. x2 is a2 plus b2 square root of 2. And a1, b1, a2, b2 all belongs to rational numbers. Then obviously x1 plus minus x2 is simply a1 plus minus a2 plus b1 plus minus b2 square root of 2, right? So since a1 plus minus a2 also belongs to Q, and b1 plus minus b2 also belongs to Q, so at least this new number system is close for the addition and subtraction, right? How about multiplication? So we can go further. For the multiplication, so x1, x2 is a1, b1 square root of 2, a2 plus b2 square root of 2, which is a1, a2 plus b1, a2 square root of 2 plus a1, b2 square root of 2 plus b1, b2, and 2, right? So we can combine them together as a1, a2 plus 2b1, b2 plus a1, b2 plus b1, a2 square root of 2. So definitely the rational number system is close to the four basic arithmetic operations. So a1, a2 plus 2 b1, b2 belongs to Q, right? And a1, a2 plus b1, a2 also belongs to Q. So that means x1, x2 belongs to real number system. Am I going a little too fast? Am I talking too fast? That's okay? So we found that the real number system is close to addition, subtraction, and multiplication, right? So now let's try division, because I'm going to repeat. I'm doing this because we need to do this again for complex numbers. So division. So x1 divided by x2. So a1 plus b1 square root of 2, a2 plus b2 square root of 2. Oh, it looks complicated, right? I told you when the things looks complicated, what do? Do nothing, right? So doing nothing sometimes simply add 0 or multiply by 1. So let's try to do something, do nothing. So a2 minus b2 square root of 2 and a2 minus b2 square root of 2. So I multiply by a2 minus b2 square root of 2 and divide by the same thing. So it's basically just multiply by 1, right? So I haven't done anything. But multiplication of this actually can change a lot, especially in the denominator. This is called denominator. This part is called denominator. So nominator is 분자, denominator is 분모. So let's try to see what happens in the denominator. So the first one is easy, a to 8, right? So a2 square plus a2b2 square root of 2 minus a2b2 square root of 2 minus 2b2 square, right? That's your denominator. And nominator is a1, a2 plus b1, a2 square root of 2 minus a1, b2 square root of 2 minus 2b1, b2. So apparently, these two are cancelled each other. So denominator become pure rational numbers. So it becomes a2 square minus 2b2 square, a1, a2 minus 2b1, b2 plus b1, a2 minus a1, b2 square root of 2. You can actually rewrite the whole thing minus 2b2 square, a1, a2 minus 2b1, b2 plus a2 square minus 2b2 square, b1, a2 minus a1, b2 square root of 2. Because b1, so rational numbers are close for basic arithmetic operations, right? So the first part, this part belongs to Q, right? And this part also belongs to Q. The coefficient of square root 2 becomes rational numbers, and also we have rational numbers. The division actually yields real numbers. So the whole thing becomes real. So irrational numbers, real numbers, are known to be closed for basic arithmetic operations. So we can conclude that, should I go a little slow? Maybe this topic is too easy for you, right? So real numbers are closed for basic. This is called for basic arithmetic operations. So basically, all the Newton's calculus and 17th century's advance in mathematical analysis and algebra are based on the finding that these real numbers are closed to for basic arithmetic operations called addition, subtraction, multiplication, and division. And for many years, many mathematicians lived happily ever after because everything is now set, right? So you don't have to worry about that until a few hundred years later. So there is an old saying that history repeats itself. Who said that? Anybody knows that? Who said that particular phrase? History repeats itself. E.H. Cobb. No ring a bell? 역사는 반복된다. History repeat itself. E.H. Cobb. So actually we have uneducated bunch of students, basically. So around 17th century, many mathematicians asked the question. It's same question as Pythagoras did about 2,000 years ago. The 17th century, they asked if there is any number such that x squared is minus 1. So the 17th century mathematicians asked the following question. Is there any real numbers? If you square it, it gives minus 1. Do you know any real number that satisfies the following condition? No, there's no real number such that. So it's the beginning of complex number systems, and maybe you can take a break for a few minutes before we continue. How about that? So I'll turn off. So the first person, according to the history, is maybe speculation to find a number that satisfies the following property is Descartes, René Descartes, in 17th century. René Descartes designated I as a square root of minus 1, and he said I square is minus 1. And he called this number as an imaginary number. He called I as an imaginary number. So it's an imaginary number because it doesn't exist really, but it only exists in our imagination, in our mind. So he defined this I as a square root of minus 1, and he called this an imaginary number. And after Descartes, the two mathematicians has done extensive work to develop the complex variables theory that we have now. Their name is Leonhard Euler, (1707 to 1783), and Carl Friedrich Gauss. The two names are very important in the history of mathematics, especially related to the. So they actually started the number system called complex numbers. So x and y belongs to the real numbers, and we call the new set of complex numbers as C. So the first step they did was this complex number system is indeed, again, closed to the four basic arithmetic operations: addition, subtraction, multiplication, and division. Because once you can set up that the complex number system is closed to the four basic arithmetic operations, then you can define the complex functions. So we are following the steps. So let's say C1 is x1 plus iy1, Z2 is x2 plus iy2, x1, x2 are real numbers, y1, y2 are also real numbers. So let's try to add them together if they are also complex numbers. Z1 and Z2 belongs to complex set of complex numbers. So z1 plus z2 is x1 plus iy1. x2 plus iy2 is x1 plus x2 plus I y1 plus y2. So since this belongs to real number and this belongs to real number, so whole thing become complex numbers. So Euler found that the complex number system we can define addition at least. And then he continued. So next step is subtraction. It's so easy, right? So z1, oh, sorry. Let's switch back to the blue. So z1 minus z2 is x1 plus iy1 minus x2 plus iy2. And then it can be combined into this x1 minus x2 plus iy1 minus iy2. And it turns out that this, again, x1 and x2 are real numbers, right? And, oh, sorry. So maybe I have to write it again. So x1 minus x2 plus I is common factor, so you can put them together. Because here we have I here. So we can put I as common factor and put the parenthesis inside y1 minus y2. Then this is real numbers. This is real numbers. So whole thing is complex numbers, right? The multiplication z1, z2 is x1 plus iy1, x2 plus iy2. So simply just multiply x1, x2 plus I, y1, x2 plus I, x1, y2 plus I square, y1, y2. And I square is minus 1, so we have x1, x2 minus y1, y2 plus I, x1, y2 plus y1, x2. So obviously this is a real number, right? And also this is a real number. So everything is, again, belongs to complex numbers. So Euler found out that complex numbers are close to addition, subtraction, and multiplication, right? How about division? Can I move on previous page? Division. You need to, so z1 divide by z2 with z2 is non-zero. So this is x2 plus iy2, x1 plus iy1. Oh, so we have a complex number in the nominator and denominator. Make our life miserable, right? So what do? We somehow simplify this expression. So how do we simplify that expression? By doing nothing. Doing nothing means sometimes you can add 0, and sometimes you can multiply by 1. So let's try by doing multiply by 1. And how do you multiply by 1? You multiply something and divide by the same thing, right? So So it's a very simple trick in mathematics. So if you know those tricks well, that will make your life much easier. So let's just multiply by 1. So that is, you multiply by something and divide by exactly the same thing. So I have a hunch that maybe I can multiply by these numbers. Then maybe, hopefully, our life is easier. So let's see what happens. So in the denominator, let's calculate the denominator first. So x2 times x2 is x2 squared. Second term is x2 times iy2, so that becomes ix2y2. How about this? x2 times minus iy2 is minus ix2y2. And multiply by this iy2 times minus iy2. So it's something like this. I times minus I times y1, y2, right? And for the denominator, x1, x2, we have I x2, y1 minus I x1, y2 plus we have I y1 times minus I y2. So I times minus I is minus I square is plus 1, right? Because I square is minus 1, so you have a minus I is plus 1. So with this help, we can simplify, and these two cancels each other. We have x2 square plus y2 square, x1, x2 plus y1, y2 plus I x2, y1 minus x1, y2. So again, I'm going to separate two parts as x1, x2 plus y1, y2, x2 square, y2 square plus I x2 square plus y2 square, x2, y1 minus x1, y2. So apparently, this is a real number, right? So this belongs to real. And apparently this also belongs to real. So real number, and we have I here, so this belongs to complex numbers. So we simply found out that the complex number system is also close to the four basic arithmetic operations. So it's a third number system that was close to the four basic arithmetic operations. So what was the first number system? That was close to the four basic arithmetic operations. What was the first one? We just did 1 hour ago, so you should be able to remember that. Rational numbers, right? What was the second one? Real, right? Correct. So this is third one, correct? Okay. So far we know that 3 number systems only are close to the 4 basic arithmetic operations. There may be another one, but I don't know. So we had a very important discovery that the set of complex numbers is closed to the 4 basic arithmetic operations, which is addition, subtraction, multiplication, and division. So this result implies that we can define complex functions. So we can define complex functions, and which is subject of this new topic for this semester. So we are going to study functions of complex variables and differentiation and integration. So the whole thing, so I'm going to call this as complex analysis. And if you think I'm going a little too fast, maybe you can make me slow down by asking some questions. No intention of slow down. Perhaps I will. So before I'm going to moving on to the next topic, maybe I like to break the ice. So maybe. So we found that the complex numbers are closed for the 4 basic arithmetic operations and ready for defined complex functions. But how can we do that? So before we do that, there is another approach of representing complex numbers by geometry that was actually pioneered by Descartes, that is replacing in two-dimensional geometry, coordinate x and y. So Descartes was trying to represent the complex value, complex number, in terms of two-dimensional coordinate system, geometry. Distance is r, angle is theta. And r is square root of x squared plus y squared. Theta is arctangent y over x. Previously, I was not able to succeed in copying and paste, so this time I'll try it again and see what happens. So what I'm going to do is this, because I'm going to use this many times. And push that long time. It's supposed to work. Oh, maybe I should push this. No. Let me try this. Uh-oh. What happens? Okay, let's. Oh, it's not working. Just turn off the record. Repeat again. So. So Descartes actually represented the complex number in the coordinate system r and theta. So this is actually x. This is called y. So z is x plus y, and r cosine theta is I r sine theta. Here r is square root of x squared plus y squared, and theta is tangent, arctangent y over x. And this part is sometimes called real z, and this part is called imaginary z. So real part or imaginary part? Real part, imaginary part. So that means real z is x, r cosine theta. Imaginary part of z is y, r sine theta. Sometimes it is known as polar representation. Then this polar representation can do a very nice thing. So I will continue. So you still figured out why theta enhanced and theta wasn't left? No? Okay, maybe too much for one day. So assuming I have two different complex numbers, z1 and z2. c1, x1, y1, c2, c2, oh, sorry, c2, x2, y2. So it can be represented by different angle and distance. So this is r1, this is theta 1, this is called theta 2, this is r2. So z1, z2 actually so of course we have done this before, right? So we know how to express this in terms of x1, x2, y1, y2. But since we are using polar representation as another tool, so let's try to see if what happens. This is r1 cosine theta 1, I r1 sine theta 1, r2 cosine theta 2, I r2 sine theta 2. So r1 and r2 can be pulled out together, right? So r1, r2 cosine theta 1 plus I sine theta 1 cosine theta 2 plus I sine theta 2. So this is r1, r2, and we can just multiply them together. Cosine theta 1 times cosine theta 2, right? So cosine theta 1 cosine theta 2. How about this imaginary part? I sine theta 1 times I sine theta 2. It becomes I square is minus 1. So it becomes minus I sine no I sine theta 1 sine theta 2 plus I sine theta 1 cosine theta 2 cosine theta 1 sine theta 2 It would be really nice if we can make a copy, but I'm afraid I still figured out how to do that. So I thought I did, but it didn't work. So I have to memorize. So it would be nice if I can just make a copy of this, but cosine theta cosine minus sine sine cosine sine. So it becomes r1 r2 cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2 plus I sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. So let's compare with the same. This must be familiar to you. What is cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2? Cosine theta 1 plus theta 2, right? How about sine theta 1 cosine theta 2 times cosine theta 1 sine theta 2? So sine theta 1 plus theta 2. So apparently, the multiplication of two vectors can be represented as cosine theta 1 plus theta 2, I sine theta 1 plus theta 2. Right. So the magnitude is multiplied, angle is added. So we are going to do a very simple case. When this is 1, special case, when r is 1. Then, in this case, cosine theta plus I sine theta, right? Then z square is z times z will be simply cosine theta plus theta I sine theta plus theta, right? Because we found that the multiplication of the complex number is you add two angles and you multiply by the magnitude, the radius. But since we have set r is equal to 1, so we only need to worry about the angle. So if we square it, it becomes 2 theta, 2 theta, right? How about z to the cube? Still addition, right? I still haven't figured out how to generate the form without keep repeating, selecting the white versus yellow. So g to the cube is z squared times z, right? So it can be again cosine 2 theta plus theta, I sine 2 theta plus theta is cosine 3 theta plus I sine 3 theta plus theta. It's actually cosine theta plus I sine theta to the cube, right? That's the cube. So we can continue 3 theta. Oh, sorry. So we can actually continue. So g to the n cosine theta plus I sine theta to the n is simply cosine n theta I sine n theta. It has a special name called the Moivre's theorem. Moivre의 정리. Heard about that? No? So at least one thing is consistent, right? Nothing is heard about. So this is called the Moivre theorem. So this is a very interesting property that, so if z cosine theta plus I sine theta we don't know, but if it is some function of f theta, then z to the n is f to the theta to the n. Turns out to be cosine n theta plus I sine n theta is f n theta. So if we want to represent this cosine theta plus I sine theta as some function of f theta, then if you take a power of n to the z to the n, it's basically f to the n, right? But it turns out that the result is f cosine n theta plus I sine n theta is f n to the theta. So we need to do this again. So f theta to the n, f n theta. So what kind of function satisfy this relation? If you take the power of n, same as it's n times of its argument, we actually encountered this kind of function before. If you take many times, n times, become something of n. Exponential function, right? So possible candidate is f theta must be exponential alpha theta, some function of theta, right? Alpha can be complex numbers, but since we found that this complex number system is now set so close to the four basic arithmetic operations, we can define complex functions. And you know how to represent exponential functions, right? Exponential functions, exponential x is what? In Taylor series, 1 plus x. You know this, right? So, likewise, exponential alpha theta must be 1 plus alpha theta plus 2 factorial alpha square x square, 3 factorial alpha cube x cube, theta, 4 factorial over alpha fourth, theta fourth. On the other hand, f theta is simply cosine theta plus I sine theta, right? That's one side of the expression. So if we represent this using Taylor series also, then it is become minus theta square over 2 factorial, 4 factorial over theta 4, I theta minus 3 factorial over theta cube plus 5 factorial over theta 5 plus plus plus. So this 2 has to be the same. So this 2 has to agree with each other. Right? So it's obvious. Alpha is, if you compare with this, alpha is simply I. Yes. So we now found the formula. Probably the most profound formula is exponential I theta is cosine theta plus I sine theta. That's very important. So can I move on? You'd like to have some more time to copy this equation? many pages do I have? Is 18. 20. So we have a very nice expression. So exponential I theta is cosine theta plus I sine theta. This is one of the most important formula. Actually, second important formula known to us. One was the coil times coil times coil that we studied in the few weeks ago. But this is also very important. And it has a name. It's called Euler's formula. And the wave equation, I mentioned briefly before, the solution of electromagnetic Maxwell's equation is given by exponential minus I kx minus omega t. Now we can represent this, and if you go back to previous lecture note, then we have curl times curl gives wave equation, and the solution is actually given by this. So this is a solution of wave equation. And we know that because of Euler's formula, now this solution can be represented as cosine and sine. So exponential I kx plus omega t is cosine kx minus omega t plus I sine kx minus omega t. So that means the importance of the solution is if this is constant, then as time goes by, the peak of the solution is moving with time. So for example, assuming the kx minus omega t is equal to 0, right, then position becomes proportional to t. The signal is moving with time. Then this wave is propagating. In space. So Euler's formula actually allows the solution of the wave function is a propagating solution. So according to the one of the Holy Bible says there was a light in the beginning, but light exists because of this Euler's formula. So if Moses actually knew a little bit more math, then when he wrote Bible, he might have written down that there was a Euler's formula in the beginning. That was a more mathematically correct expression. Then there was a light. So this Euler's formula is a very profound effect. It allows that the light is propagating solution, and it actually is possible of this space-time curvature created by this current universe allows this formula. So Euler's formula is related, maybe related to this, I don't know, this current space-time structure of this universe. Maybe not. I may be wrong. But that's my belief. So Euler's formula is very profound effect. So we can exploit these properties a little bit further. So I'm going to make 21. So exponential I theta is cosine theta plus I sine theta, right? What if theta is minus theta. Then exponential I minus theta can be written as cosine minus theta plus I sine minus theta, right? So that is cosine. However, cosine minus theta is still cosine theta. But sine minus theta is minus sine theta. Right? So we have two formulas. Exponential I theta is cosine theta plus I sine theta. Exponential minus I theta is cosine theta minus I sine theta. So we can add them together. Say 1, 2. So 1 plus 2 gives exponential I theta plus exponential minus I theta is what? 2 of cosine theta. So cosine theta is actually exponential I theta plus exponential minus I theta divided by 2. So cosine theta can be defined in terms of Euler's formulas with a complex exponent. Maybe we can take a break for a few minutes. How about that? So I'll talk about that. Okay, so let's continue. So 1 minus 2 exponential I theta minus exponential minus I theta gives cosine theta plus I sine theta minus cosine theta plus I sine theta is 2I sine theta. So that gives sine theta is exponential I theta plus exponential minus I theta divided by 2I. So we have cosine theta is basically given by 2 over exponential I theta plus exponential minus I theta. Sine theta is 2I exponential I theta minus I theta. If theta is given by some zeta, this is zeta, then cosine I zeta is exponential I zeta plus exponential minus I zeta. It's simply 2 over exponential minus zeta plus exponential zeta. That is cosine hyperbolic zeta. So we have cosine I zeta is cosine hyperbolic zeta. There's a very interesting relation between the complex numbers and real numbers. And I can continue with the sine I zeta 2I exponential I zeta minus I theta is 2I exponential minus theta minus theta, or minus 2I exponential theta minus theta is minus 1 over 2I to sine hyperbolic theta. Right? So it becomes I sine hyperbolic theta. So sine I hyperbolic theta is I sine hyperbolic theta. So we are getting there. So using these two properties, we can define cosine z, x plus iy, is by the definition 1 over 2 exponential iz plus exponential minus iz. And works. Finally succeed. So we can continue this. I figured it out finally. Great. I x plus iy plus exponential minus I x minus iy. So it becomes 1/2 exponential ix minus y plus exponential minus ix plus y. So 1/2 exponential minus y cosine x plus I sine x exponential plus y cosine x minus I sine x. So it becomes, we can combine them together with cosine x. We have cosine x and exponential y plus exponential minus y plus I sine x 2 over exponential minus y minus exponential y, right? So cosine x cosine hyperbolic y minus I sine x sine hyperbolic y. Let me check if this formula is correct. Yes. So we have a very interesting result. That is cosine z is cosine x plus iy is cosine x cosine hyperbolic y minus I sine x sine hyperbolic y. On the other hand, we can check that if we assume that if complex this addition 가법 정리 is satisfied in complex domain, we can say this way: cosine x cosine iy minus sine x sine iy. if that is if addition theorem holds in complex domain. Then we know that cosine Iy is cosine hyperbolic y, right? We just showed that before. Minus sine x. Sine Iy is I sine hyperbolic y. Y. Right. So we found that, so they're the same. This result is same as this. So that means the trigonometric addition theorem you learned in middle school is also valid in complex numbers domain. So we found that trigonometric addition theorem is also valid in complex domain. Then we can just use this to express other function of complex numbers. So I can continue this with the. Looks like you are burned out. I've been doing too much thing today. Just be patient. Just do a little bit more and let's quit. So we can actually use this property to express sine z. So sine x plus iy. And the easiest way is using just trigonometric theorem. So that is sine x cosine iy plus cosine x sine iy. So that's sine x cosine hyperbolic y plus I cosine x sine hyperbolic y. Right? So I can give you the following homework. Express cosine hyperbolic z, sine hyperbolic z, and cotangent tangent hyperbolic z. So homework means you just do at home and don't turn in. And tangent z, let me see, I must have something in my note that says sine, which is cosine, right? So tangent z can be defined as cosine z, sine z, right? So that is cosine x, cosine hyperbolic y minus I sine x, sine hyperbolic y, and sine x cosine hyperbolic y plus I cosine x sine hyperbolic y. And another homework is simplify. It's another homework. So simplify means make this denominator real numbers. It could be really exciting, actually. So I can do that. Let me see. So, homework. So I'm going to do it in the class, but also I ask you to do at your home because it's a very good exercise and also my favorite problem for the quiz. So let me try this again if this works. Okay, so what did I do? A little bit. There's something should appear. Nothing is appearing. Oh, edit. Okay, add to the clipboard and delete. It works. Great. And next page. Clip art. And it has to be this one, right? And I can move it. Okay. I can move this. Oh. Works like a charm. So it looks extremely complicated. So what do you do? Do nothing. How do you do nothing? Multiply by 1. So let's try to do that. So actually I think I figured out how to make a cut and paste, but it's a little bit awkward. So times. Okay, what do you like to multiply? Cosine x, cosine hyperbolic y plus I, sine x, sine hyperbolic y, cosine x, cosine hyperbolic y plus I, sine x, sine hyperbolic y. Well, so let's say dxy and xy. So let's do it term by term. So let's calculate the denominator first. So dxy is, so you multiply this and this first, right? So this cosine x squared, cosine hyperbolic square y. And now by now we know that this term and this term cancel each other, right? So only surviving term is this times this. So sine square x, sine hyperbolic square y. Is there any way that we can simplify things? You can use these properties. Cosine square y minus hyperfine square y is 1. You can use this property, right? You know this. No? You don't know? So if we use these properties, then this cosine square x becomes 1 plus sine square y plus sine square x sine square y is cosine square x plus cosine x plus sine square x sine square y. However, cosine square x plus sine square y is equal to 1. So denominator can be simply cosine x squared plus sine square y, or vice versa. Denominator is a little bit more complicated, so I'm going to write down denominator and then make a copy to next page. So denominator xy. Let's say the first term first. This and this is a cosine sine x cosine x and cosine hyperbolic y minus sine x cosine x sine hyperbolic square y. Oh, that's nice actually. Plus I cosine square x sine hyperbolic y cosine hyperbolic y plus I sine square x cosine square y sine square y. And I'm going to use the trick that I just learned. So before I forget, let's try to copy this. Okay, so if I push hard enough, edit. And add this clip art and delete. Work like charm. So can I move on to the next page? Add. That is cosine square x plus sine hyperbolic square y. Okay, so this clip art. This must be the first one. Okay, very nice. So I can move this here and make it large. Oh, even better. So I'm getting good. So we can actually combine them together as a sine x cosine x, and it becomes cosine hyperbolic y minus sine hyperbolic y plus I sine square x plus cosine square x sine hyperbolic y cosine hyperbolic y. And this is 1, right? This is 1. So actually sine x cosine x plus I sine hyperbolic y cosine hyperbolic y. So tangent to z is nz over dz and xy over dxy is simply, okay, let's know what do we know. Sine x cosine y I sine hyperbolic y cosine hyperbolic y. Denominator we don't remember, so we have to go back. So cosine square x plus sine hyperbolic square y. Let's check if my result is correct with my previous note. Sine x cosine x y plus I sine hyperbolic y. Something wrong? Sine cos. Oh. So it has to be x, right? sorry. It has to be x. So sine x, cosine x plus sine y and y. So this is our result. So I can ask you to calculate another homework, maybe tangent hyperbolic z as a homework. There are a bunch of homeworks I can give you. Cotangent z is sine z over cosine z. This is our homework list. And secant z is maybe easy. Cosecant z, sine hyperbolic z. What else? Secant z, cosine hyperbolic z. CHZ, sine hyperbolic z, and cotangent hyperbolic z. So there are many important trigonometric functions and hyperbolic functions in complex variables. So I like to give them as homework. So you just do it at home, but don't bother to turn in, because you will have plenty of chance to writing those formulas in your quiz. So perhaps I can stop here today. What do you think?